Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're tackling a problem around the idea of acceleration, velocity, position, dynamics. This is the realm we're talking about here, and it's a simple problem, uniform acceleration. We've done a problem with the plane just before. If you want to check it out in the corner here, and we're going to use the equations that we've derived in that problem, right? Simple equations, but we're going to use those nonetheless. So if you're interested, just check them out to see where they came from. So problem 11.34, a motorist is traveling at 54 kilometers per hour when she observes that a traffic light 240 meters ahead of her turns red. The traffic light is timed to stay red for 24 seconds. If the motorist wishes to pass the light without stopping just as it turns green again, determine the required uniform deceleration of the car and the speed of the car as it passes the light. Okay, so it's a simple structured problem. There is this person. She is with a V naught at 54 kilometers per hour. So at time equals 0, V, which equals V naught, is 54 kilometers per hour. And she has a distance of 240 all the way until she reaches the stoplight. But the light is red and she wants to cross on green. So basically, because somehow she knows it's 24 seconds that this light stays red, she wants to know at which velocity, at which deceleration she needs to apply to the car, uniform deceleration, so that when she arrives at the light, she doesn't have to brake completely and stop. She can just continue on. It's a given that's not going to be 54 kilometers per hour. She's going to have to slow down the velocity of the car to be able to do that. Now, what do we need to pay attention to? Well, first and foremost, this velocity is given in kilometers per hour, and these guys are given in meters and seconds respectively. So there's a mismatch of units there, right? So the first thing you need to do is you need to decide on whether you want to do the conversion of the velocity into meters per second, or if you want to convert the distance and the seconds into kilometers and hours respectively. Okay, and what we're going to do in this video, we're going to do both, because you shouldn't be afraid of any of these, but obviously you can choose whatever you feel more comfortable with. Then we need to find out what is so very important information here. What is the required uniform deceleration, right? And the uniform is the key word there, because that means, once again, just like in the previous problem, that the acceleration is not a function of time or velocity for that matter, or position, right? So it's not changing. And it's going to be a single value. So we can use the same equation as before, because when we integrate, right, again, talking about the previous problem, when we integrate, that a can come out of the integral. Okay, so we are to find out first, what is the acceleration of the car? So a equals what? And what is the speed as it passes the light? So what is the speed? Let's go ahead and call this position here A, this position B. It wants to know what is at x equals B, V equals what? Another way of asking the same question is at time equals 24 seconds, V equals what, right? Because we know that we want it to happen exactly after 24 seconds. All right, so we're going to do, like I said, both, and let's start with converting the velocity, okay? So method, let's call it part one of the solver, or whatever we want to do. So to do that, so what we're going to do is call it velocity conversion. Velocity conversion, okay, convert. So what we're going to do is we're going to convert our initial 54 kilometers per hour into meters per second. And we always do unit conversion the same way, because this way we never miss. It's one at a time, and we're thinking, okay, if I want to have 1 hour here at top, 1 hour is exactly the same as 3,600 seconds, right? 3,600 seconds, right? And when I do this, my parenthesis is 1, and therefore I'm multiplying by 1, so I'm not altering anything, right? And here, I know that 1 kilometer, which is what I have in the bottom to cancel the kilometer, is same as 8,000 meters. So all I'm doing is multiplying by 1,000 and dividing by 3,600. What's going to happen with my unit is that kilometers and kilometers are going to go away. Hours and hours will go away, and I'll be left with meters per second, just as I planned. Right, so this turns out to be 15 meters per second. And now we're in a good position to go ahead and say, okay, so I know that the way that my position varies, the change of my position is equal to my initial velocity times the time plus the acceleration times squared over 2. And again, we've derived this from scratch using our basic principles of acceleration is just how the velocity varies with time. All right, so because it's uniform velocity, we can use this equation. And really what we're looking for here is, okay, when this guy is 240 meters, that's the delta I'm looking for, and this guy is 24 seconds, knowing that this guy has an initial velocity of 15 meters per second, what will be the acceleration for all this to come together, right? So very straightforward. I have 240 meters, then I need to travel with an initial velocity of 15 meters per second in 24 seconds, plus the acceleration of 24 squared over 2. So note the only unknown here really is the acceleration. No tricks, no problem, right? So this means that minus 120 will be equal to my acceleration times 24 squared over 2, which means that my acceleration will be negative 0.4166666666 forever. So go ahead and approximate this guy to 7 right here. Okay, and that is in meters per second squared. Okay, and we can check that because over here we have meters on this side. Over here we have meters per second times second, so it's meters 2. So we have meters and multiplying by the 2. There's no unit there. And then we're dividing the meters by second squared, right? So seconds squared. So we can do it one at a time if we wish. Let's go ahead and, from this equation here, look at the units. Over here we have meters, which equals meters per second velocity times the seconds plus the acceleration that we're trying to figure out, which is times the seconds squared, and 2 has no dimensions, right? So then here, this becomes meters, and we're saying the meters there is subtracting. So therefore, when we get to this next here, to this next line here, what we have is meters equals our acceleration times second squared. And then we're dividing everything by the seconds. So therefore, we're left with meters divided by second squared is the unit of our acceleration, which is great. So that's it. That's the answer. It needs to decelerate uniformly at a rate of 0.4167 meters per second squared. Brilliant. That's half of it. The other half is what is the velocity when it crosses it? And that's super straightforward because we know that acceleration is just the rate at which the velocity changes the time, right? And in this case here, we have a dt equals dv, and we can integrate from 0 to t, and we can integrate from v naught to v. And because this is a constant, we know it's a constant, it can come out of the integral, which means this integral is super simple. It's just at equals v minus v naught. So therefore, if I'm looking for this guy here, all we need to do is solve for it. It'll be v equals my v naught plus my at. As simple as that. We know everything we need to know here, right? So if I want to find out what is at t equals 24, which is exactly when she crosses the red light, all I need to do is velocity will be equal to my initial velocity, which is 15, minus plus my acceleration, which we know now is negative 0.67 times the 24. And if you recall, we just literally divided by 24 just on the previous step. So this is going to turn out to be my 10, right? So this is going to be equal to 15 minus 10, and therefore my velocity equals 5 meters per second. So that's the velocity when she is crossing the red light exactly.